I'm going to describe how to use an interactive simulation that models diffusion and reaction in a catalyst pellet. So the idea is that surrounding a pellet, we have a concentration of a reactant, gas phase, and this reactant diffuses into this porous pellet, and as it diffuses, it also reacts. So as we look at a concentration profile within the pellet, concentration decreasing as we move towards the center because of reaction. Now, what the simulation allows you to do is change the radius of the pellet, the rate constant of the reaction, and the diffusivity, and then it calculates what's the overall rate, Thiele modulus, the effectiveness factor, and let's talk about what each of those are. So the Thiele modulus, which corresponds to the rate of reaction over the rate of diffusion, is the radius, the rate constant, and an effective diffusivity. So we're given a diffusivity that we can change on the slider. The effective diffusivity is that diffusivity multiplied by a couple terms and divided by 1. So let's talk about those. This is tortuosity. That fact is not a straight path into the center. This is porosity. In this case, this is 0.4, and the tortuosity that we use is 3. And this is a constriction factor of 0.8. So the effective diffusivity is going to be smaller than the diffusivity report here. The effectiveness factor, which is what we're interested in calculating, is what's the rate of reaction inside that pellet divided by the rate of reaction if everything was at this concentration. In other words, if the concentration profile was this dashed line. And keep in mind, this is just a 2D representation of a 3D volume where we have reactions. So the rate constant, first order, assuming everything's at that surface concentration, and then the volume of the sphere. And so this rate of reaction is basically integrating over the volume of this concentration. And the equation for first order relates the effectiveness factor to the Thiele modulus, that's squared, the hyperbolic cotangent Thiele modulus minus 1. So this is what we calculate here. And so let's look at how this effectiveness factor changes as we change parameters. We'll look at the interactive simulation. So here is the interactive simulation. If we were to decrease the radius of the pellet, notice the concentration is going up quite a bit. We're decreasing the diffusion distance, and the effectiveness factor is increasing significantly. So let's go back to a larger. If I increase the rate constant, now the concentration is dropping, the effectiveness factor is decreasing. If I increase the diffusivity, then the effectiveness factor increases and the concentration increases because this competition between diffusion and reaction increase the rate that it diffuses in, keep the rate of reaction, rate constant the same, then I can get a much higher effectiveness factor. And so to use a catalyst effectively, we want a high effectiveness factor.